Okay, my name is Don Capps. I'm the author of IOZone as well as SPEC SFS2014. I'm also the chair of the SPEC SFS slash storage subcommittee. Um, so yesterday we went through the process of setting up the clients, installing some software, setting up various pieces of equipment. So today we're going to talk a little bit about the next step, which is we need to set up our storage system that we're going to be testing so that it will actually run the test successfully. So with each storage system, vendors have a published, in general, they have a published best practices guide that tells people how to set it up, how to configure it, and how to tune it, okay, so that it will behave well. So there's no common, shared set of tunings that apply to all storage systems. So you'll have to get the storage best practices tuning guide from the manufacturer. All right. We need to make sure that when we're going to run the benchmark, it's going to create a bunch of files and directories and consume quite a bit of space. And you can calculate that space by looking in the user's guide, or earlier in the presentation, it told you how much space, physical disk space, do you need for each load increment on each of the 4 different workloads. So you need to make sure that you've got sufficient disk space allocated on the storage system so that it literally won't run out of space in the middle of a test, because it's kind of a bummer to run, 6, 8, 10 hours and then discover you ran out of space and have to start over. Okay. The next thing you need to do is, in general, you would like to make sure that as the load is scaling up, that it generates traffic across all of the various network interfaces and all of the various spindles that, or SSDs or whatever you've got down there in the storage system. If you have multiple network controllers and multiple disk controllers, you would like for all of the workload being presented by the clients to cross all of those data paths so that you get as much parallelism as you can. All right. That's done by editing the client mount point string that's inside the configuration file, the SFS configuration file. Let me pull that up so I can give you kind of an example. So here we are, SB2, down in the bin directory. We'll go look at our RC file, and there's that string, the client mount point string. So in this case, I have a load of 5. All right, so I know that I'm going to exercise 5. My first load point is going to exercise 5 of these paths. So it's going to exercise the remote client, whose name is CentOS7M1, and it'll be going after the directory, the mounted directory from the storage system that's at /mnt/freenas/test. And then the next client is CentOS-M2, who's going to be talking to the same directory. Then the next client is M3, who talks to the same directory, then M4, who talks to the same directory, then M5, who talks to the same directory, and then on your next load point, it's going to talk to a different directory. Each of those 5 clients is going to talk to test1 subdirectory. Now, they don't have to be subdirectories. These could be completely different mount points. So you could have 4 different volumes that are exported over 4 different NFS mount points, or a dozen or 1,000, however many you want, and you have your processes and your clients basically round robining across all of the storage, and you're specifying how you want that as the load increases. How do you want it to scale up, and what interfaces do you want it to cross? Now, if you really wanted to get it extremely balanced, then you might say, well, I'm going to change this little layout here so that I went M1 goes to test, M2 goes to test 1, M3 goes to test, M4 goes to test 1, M5 goes to test, M1 goes to test 1. M2 goes to test. You see how I'm doing this? I'm generating a round robin across both of them. So test 1, test 1, test 1. So that would be an even more balanced load than the former. The former said the first 5 load first 5 load increments go across the storage system whose name is, test. The next 5 go across test 1. As we're in the latter, I said, well, I'm going to rotate back and forth as I increment my load. I'm going to make sure that I use everything that's available for every load point instead of having them come online as I increment load points. Now, in some storage systems, this will make no difference at all because these could be there could be one giant pool of volumes that are all aggregated together and striped together and present a single mount point. And everybody could use the same mount point, and you're still uniformly distributed because you're relying on the storage system to actually cross all those data paths internally. All right. Now, it's also possible that these clients, when I specified client CentOS M1, he's going through this mount point whose name is mnt/freenash/test. That's a mounted directory. So literally before you started the test, you booted up all the load generators, you got them all ready to go, and then you mounted the file systems so that they would appear in these names, all right? But that doesn't necessarily mean that they all traveled the same path. So CentOS 7M1 could have gone over a different data NIC than CentOS 7M2. In fact, it's possible that when CentOS 7M1 appears the next time in the list, that he could be going to a mount point that is indeed over a second NIC from that client. So this gives you the ability to, through the combination of mounting your file systems on your client, you get to choose what data NICs you're going to be using, and then here you can choose which mount points and which clients you're going to be using to generate load. So you have really good flexibility on ensuring that you're going across all of the different data paths to get from your load generator down to storage and touch all those data paths equally, which in general is the best way to get good performance, is parallelize everything as much as possible. All right, now we want to make sure that we've got enough space to run all this stuff. So if we were to go out here and look, I'm going to actually go out and do it here so you can see what it looks like. So this configuration file says I'm going to be going and touching the VDA workload. And we say, oh, well, if we go back in our presentation, we know that VDA is going to require 10 megabytes of space per load increment. So 10 megabytes per load increment. Well, on that test that I was just showing you, he starts at 5 and he goes for 10 runs. So his last load point will be 50. So if I know I need 10 megabytes per load point and I got 50 as my highest load point, then I really need to have 500 megabytes of free space available before I start the test. So that's how you sanity check that to make sure that you're not going to run a test and then halfway through it run out of space. And the same is true for all of the workloads. They each have a list of how much space they need. Software build needs 400 megabytes. Oh, I'm sorry, that's load. Oh, I got this wrong page. That was memory size. Whoops. Hold on, let me go back. Got to go find the size. Go back. Where is it? Oh, okay. Well, I'm going to have to go down to the man page. That's the wrong one. I'm jumping forward. I'm sorry. Here it is. VDA is 24 gigabytes per load increment. So 24 times 50 would be how much space you would need for your highest load point. The previous number was how much memory do you need in the client. This is how much physical disk space do you need on storage. So I would need 5 times 24 and add a 0. So that's how much space I would need. So for each of the different workload types, there's a different amount of space that is going to be required per load increment. And this is how you calculate how much space you're going to be using. And these numbers are all found in the SFS 2014 User's Guide as well. Okay. So that's how you configure enough space for all of the workloads. Now, once you got that all configured and you get your mount points straightened out, then we're going to actually configure the SFS benchmark. So what I like to do is, in the tiny print here, right underneath the make 4 copies, there's some tiny print. That's the full path name to the configuration file that you will start with. And I like to copy that thing down and rename it to something like the SFS-RC file. And then here I said make 4 copies of this thing and give them different names. So you've got the SFS-RC file for when you're going to run the database workload, another one for when you're going to run VDI, and another one for when you're going to run VDA, and so forth and so on. And you'll see why I say make 4 copies here in just a minute. So one of the things that you have to configure inside of the configuration file is what is the name of the benchmark that I'm running. So if you have a file whose name is SFS_RC_SW_build, then inside that file you would modify this benchmark string to say this is the one that's associated with running the software build workload. And the same for each of the 4. So you'll have 4 RC files. Each one points at a particular workload that you're going to run. And each one may require different mount points. And each one may require a different load value and increment of load value. And they're all going to need at least 10 load points. The number of runs will be 10 or more. But each one will be different for what is the maximum load that your server can handle, right, for each given workload type. They're very different. So the software build workload is gazillions of tiny little 16K files, and there's millions and billions of them, and it's a metadata intensive workload versus the VDA, which is a very large, multiple gigabyte, very few files, but they're very large. And it's doing a lot of sequential I/O. So those are very different workloads. So your load increment and your initial load value and your load increment are going to be different depending on what workload you're running. So when you're configuring this, like I said, I went through the example there of the client mount points where I had a client name followed by a colon followed by his mount point where you want him to test, and then space delimited, the next client name, his mount point. If you're running the benchmark on top of a Windows-based system, then the syntax is similar. It's the client's name, colon, and then backslash, the server's name, backslash share name, okay, that he's going to be exercising. Here's the user. When you're dealing with Unix systems, the user is the username of your account you're going to be running it under. If you're on Windows, the username is actually his domain backslash username because it is running inside of a Windows Active Directory and it is inside of a domain. So you really need to specify the domain and the username. And the password is really only needed to log into Windows systems. And in the Unix system, we set up the remote SSH with no password. So he didn't need anything, he didn't need your password, but for Windows, you actually have to specify a password. He will use that to authenticate and log into the domain. All right. So the load is start off at some interesting value and work your way up until you start getting invalid results, and then back off a little bit from that in order to figure out what your maximum load is. I usually take the maximum load, divide by 10, and whatever that number is, I set it in both load and incr load. so that you have 10 equally spaced load points. The warm-up time is optional. It defaults to 300 seconds. You can specify anything larger than 300 seconds up to a week, 1 week in seconds. So you can warm up as long as you want to. You need to make sure that before you start the test, you have the server's storage area either mounted or the share mapped onto the client node at the directory location you said you wanted it to be. All right. And I tell people, in general, if you're on a Unix machine, you probably want to put this in the clients/etc/fs tab, so that if you reboot the clients, you don't have to manually go out to every one of your clients and remount those file systems again. So that by putting them in FS tab, they'll get remounted automatically. And if you're on a Windows system, just say, yes, remember my credentials, make this a persistent mount, so the next time you boot the Windows client, it comes up and automatically mounts. Now, another trick that I like to do that's probably wrong. Another trick that I like to do is not only do I mount them, but I mount them with whatever version of NFS I'm trying to test, so I know specifically what version of NFS I'm running. If you don't do that, then NFS will select the highest available protocol version from both the client and the server. So if you have NFS v4 on the client and the server, it will choose that by default. If you don't want to be running NFS v4, then you can certainly override that and set it for NFS version 3 right here. And then I also like to use a soft mount. The reason that I do that is if for some reason your storage system is offline and you reboot the clients, it's nice if you have it soft mounted so the client doesn't hang when he's booting. So here I manually mounted. I went on to one of the clients, CentOS M7 M5, and said mount my storage on /public. Okay, from /public into /mnt/test. Okay, and you would have to do that manually on every client unless you went ahead and put it in the host in the /etc/fs tab file. And I should have had this slide earlier in the deck. This tells you how much space you need based on your workload that you're running and your load increment. So it's your load increment time, take your maximum load value, so load increment times the number of runs, and say, okay, what am I going for on load? Remember, I need this many gigabytes of space per load increment. I like to check before running the test, make sure you actually have enough free space. So on a Unix box, you do something like a df. On a Windows box, you would probably look at the properties file on the storage and find out how much space he's got. Here I've got tons of space, so shouldn't be a problem. Okay, we now have the clients are configured, the server has been configured, all the mount points have been set up, and the clients now have them mounted. So we think we're ready to actually kick off a run. So at that point, when you get ready to actually kick off a run, you need to start all of the monitoring mechanisms going. So you need the power collection going, you need the S-flow collection going, and you need the environmental monitoring going all at the same time. So an example of that would be I would go out to one of my machines who is the S-flow collector. And here's my little S-flow tool. So I would say /S-flow tool -4 -L with an output to /temp /S-flow log .csv. Okay, so he's out there collecting data. So S-flow is running. I would go over to the machine that has the power meter, get him started. Notice he's saving his log in a /user/cache/desktop/power meter.csv. So he's saving all of his information in the file. And you can see the numbers are now moving around on the bottom. So he is actually collecting data right now. And then you would actually, okay, so they're starting your SFlow tool, start your power meter, start your environmental monitor. I don't have an environmental monitor in my lab, so I'm just going to pretend that I just started that one. And then in order to run the test, the way it runs in the Emerald program is there are 4 workloads, and you run them one right after another. Okay, and here's a little simple script that does that. So it says I'm going to start Python. I'm going to have him start the SFS manager, which is the management process that actually gets SFS going. I'm telling him what RC file I'm going to use. So here I'm telling him to start the software build workload. And the -s says, oh, put a suffix on this, on the results, to tell me that these are the SW build, the software build results. Okay? So he's going to run that. Then, when he's done running that, I have a little script that says, oh, let's change directory out to wherever he was generating all of his files, and then remove all those files, and then wait for it to get done. Now, I like to remove all of them in background and then say, now wait, hit the wait command and wait for them all to finish, so that you remove those files as quickly as you can. If you remove them one directory at a time sequentially, it can take a very long time. So when he finishes cleaning up, so he's run the first workload, which is software build, and then he does this little cleanup thing, and you can edit the script to make it do whatever it is that you need to do to clean up. Then he's going to start the next workload. So he's going to start the SFS VDA workload. When it's done, then he's going to clean up. Then we're going to start the VDI workload. When it's done, we clean up. Then we're going to start the database workload. And when it's done, we clean up. At that point, you have all of your results have now been captured. So you have the SFlow data, the power meter data, the environmental data, and you also have the SFS results, which are not used. The actual SFS results are not used by the Emerald program, but they are kind of handy for when you're trying to figure out what is the maximum load that my server can handle. So if I go look at the SFS results, if it's marked invalid, then chances are I went too high and I blew, I'm oversubscribing the server. So you can look at those results to kind of give you a ballpark range to help you determine what that range is that your server can really handle. So once you actually get this thing started, then it looks like this. So we'll go out there and say, oh, look, we got a system all set up, ready to go. So we got 5. We'll go ahead and use this round robin thing where I'm doing the first client goes to test, the next one goes to test 1, round and round she goes. And he's going to start at an increment of 5, and then he's going to work his way up 5 at a time for 10 runs. So if I actually start that, shoot, what was the, he's running VDA, okay. I'm going to start him running. I like to make my screen a little wider because it gives kind of a wide output. And there you go. He's getting started. Now on the VDA workload, each increment of VDA workload gives you 2 processes running. One that's doing sequential I/O, mainly writes, and the other one is doing some random I/O, both reads and writes. So he's off and he's running now. And if we were to go look at our virtualization here, I can go look at what's going on these machines. You should see your network activity go up sharply as he is now initializing the files over the network going out to the NFS storage device. So we can look at it here and see what's happening from the hypervisor's view. Or we could look at it here. Wait a minute, come on, wiggle, wiggle. He's busy. It's true. And we could look at our network activity down here, and he's sending 239 megabytes per second. Megabits per second. So you can see the network load is now, this client is generating load, and he's filling up the file system with all the initialized data set that he's going to be using for testing. While this benchmark is generating load, it goes through three various states. So the first state is it runs what's called a validation. It checks to make sure that the server that you're talking to supports all of the types of transfers that the benchmark is going to do. So if the benchmark's going to do, a lookup, he's going to ask the server, "Can you do one of those?" He gets yes. So he validates all the various different calls he's going to use during the actual running of the benchmark. If any of that fails, he stops, tells you which one failed, and says, "Go fix this," and then we can try again. Once he finishes the client validation, then he moves into the initialization phase called the init, where it initializes all of the data set that it's going to use for the benchmarking, for the measurement. When it finishes the initialization, then it'll move into a warm-up phase, where it actually just sits and does all the same work that it's going to do during the measurement phase, but it's doing it in what's called a warm-up phase, where it's not measuring anything, it's just generating the same load that will be generated in the future during the measurement phase. And the idea is to run this warm-up until all of the caches on the server have reached a steady state. So that's what he's doing. He just, he's going to go through the run phase next. Once he's finished the warm-up phase, which defaults to 300 seconds, then he moves on to the run phase where he actually starts measuring things, and he's going to run for another 300 seconds in the run phase, actually taking samples. When he's done with the run phase, then he'll exit and he'll move on to the next load point. So he's going to do this for, we specified 10 load points, so he's going to run 10 of these cycles where he validates, tests, initializes, warms up, and tests. During the initialization, warm-up, and run phases, as the benchmark is running on the console, you can see there are these heartbeats that arrive about once, I think it's once a minute. You get some kind of heartbeat to say the benchmark's not hung, it actually is alive, it is making progress. This is to keep you from thinking it's hung and shutting it down or rebooting. It'll also give you some percentages, how far along it thinks it is in this particular phase. So if you're like me, you don't really want to sit there and babysit this thing for the entire day. So you look at how long did it take to get from 30% to 50%, how long did it take to get from 50 to 80, and you can extrapolate how long is it going to take to get to finish the initialization phase, which by far is the longest wall clock time portion of the benchmark, is the initialization phase. Once he's done with the initialization phase and he moves into warm-up, that runs for 300 seconds and you're done. And then the actual run phase runs for 300 seconds and you're done. So the initialization time is the big hunk of time, then you got 10 minutes of actual test for each load point. Now, if you have a really, really, really fast server with all solid-state drives and blah, 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 then the initialization can run fairly quickly. If, on the other hand, you have 1,000 SATA drives, 5,400 RPM drives, this could take a very long time. But you can extrapolate from this percent done when it's going to finish, so you know if it's going to finish right away and you can sit there and watch it, or if it's going to take all night and you can come back the next day. Now the reason he says I've got initialization, I'm at 100% complete on client 9, and he's still getting heartbeats is because client 9 finished a little ahead of everybody else. So you're still getting initialization heartbeats from the other processes, the other clients. When they've all finished, then it'll move on to the actual warm-up phase. We can actually go look and see a lot of the network activity has died off on client 1, client 2. He's still busy doing some networking. Client 3, he's still busy doing some, well, he's just finishing up on his network traffic. Client 4, I don't really want that. He's just finishing up on his networking. Client 5, he's just finishing up. So client 2 is our guy who's still generating a lot of I/O. Okay, so that's what it looks like when it's running. I'm going to go ahead and let that just continue running. So back to the slide deck here. So here he is running away and running away. And when he finishes here's where he's starting the init phase. When he goes through the init phase and he says, "Oh, I'm done with that now. Let's move into the warm-up phase." And he'll run the warm-up phase for the default 300 seconds. And during the warm-up phase, he'll give you some heartbeats. And this time the heartbeats not only tell you which client is sending you a heartbeat, but also what is his current rate that he's doing? How many ops per second is he doing? Now the benchmark for software build is trying to achieve 100 ops per second per proc. So he's at 99.9 or 99.031, 168, 123. So he's not really warmed up right now. He's still kind of bouncing around. Right? When he finishes this warm up, then he'll start the run phase, and at that point he shouldn't be bouncing around so much. When it runs for 300 seconds by default, and when it's done running, it will print out a summary, which is what was the overall average latency for the operations that were being sent from the client to the server and back. How many operations per second did he achieve total? What was his read throughput and his write throughput, which in some cases makes sense, and in other cases it's questionable. Your read throughput, when you're dealing with software build, it's a metadata intensive workload. So it's not really reading data out of the files, it's reading the file, overhead data. And it gives you a little bit of credit, for reading those, but they're generally pretty small, so you're not going to get stellar throughput when you're reading small, tiny little random files. And then he gives you this banding thing at the bottom is basically he's giving you, of all the ops that he did, he says, I measured all of them and I put them in kind of a histogram. So band 1 of the histogram that's the system, your calls that took 20 microseconds or less. Band 1, next step is 40 microseconds, 60, 80, and he goes all the way down into seconds. So he had on this one, he had band 6, he had 39 ops that actually took 1 second to complete. So you get kind of your distribution of what your ops look like and see how well your system's actually kind of behaving. And then when he's done, he finally says, oh, look, I completed successfully, and I'm generating my summary data. So the steps that you're going to be going through in this procedure are you need to do the pre-workload calibration, which is you go through this test over and over again, increasing your load until this thing, the average latency goes through the ceiling and you don't care to measure in that part of the range, or the results are becoming marked invalid. So that's what the pre-workload calibration is let's figure out what the appropriate range is for your load increment, so that 10 steps and you'll sweep the entire range from low to all the way to the maximum that the server can sustain. Now there's an assumption that if your server is achieving its maximum throughput without getting invalid results, that hopefully at that same point or near there, you will have your peak efficiency, where your efficiency is your megabytes per second per watt of power that you're consuming. So we're hoping that those two points are close, that when the server is performing at its maximum level, it's also drawing its maximum uh, power, but you're getting the maximum work done for that power. That's possible. Those are not exactly the same, so this may it just gives you kind of a good idea of where to start your range. All right. So we're going to run each of the workloads 10 evenly spaced up to the point where it says it's not invalid, and back away so the last point is valid. You have 10 equally spaced points. We're going to collect our environmental information, our power meter stuff, our SFlow stuff, okay, our SFlow data. And if we go look right now over at this machine, so we sent it out to SFlow log. And there he is. I've got him set for every 5 seconds, send me a sample. So here are the samples coming from the SFlow collector. And kind of a point of interest here, there's a timestamp in here that tells you when did he send this, okay, sample. So you can see it was today, 12:47 and 54 seconds. And 5 seconds later, 59, and 5 seconds later, 4. But for some reason, the implementation of SFlow is such that it doesn't always deliver exactly at the polled interval that you specified. It can sometimes be off by 1. So sometimes you'll see this number not go incrementing by 5. You'll see it go by 6, and then it'll go back to 5. Right? And that makes it interesting later when you actually go to correlate this data and map it into an Excel spreadsheet, then the timestamps don't always line up perfectly, which I think there'll be a nice discussion on that later today from Patrick. All right, so we're running all that, we're collecting all our data, and when it's done, then we need to talk about, okay, the goal here is to get megabytes per second per watt, and we need to derive what are those efficiency metrics. And then we need to figure out what are the sweet spots for each of the 4 workloads. So where are you drawing the least amount of power for the most amount of ops for each of the 4 workloads? So when this thing is done, it will have the SFS results, and I'll go through and show you what those look like. It will have, and I like to save these someplace. I use these for pre-calibration work, so I can figure out, what's the right range. And then we'll have our SFlow output and our power monitor output. So let me show you what some of those results are going to look like. Hope I have some laying around. I may not. Yeah, I don't have results yet. Each time it finishes a load point, you'll get a set of results uh, that appear in the results directory. We just haven't finished a single load point yet, so he's still off initializing. We'll get back to that. All right. So let's take a look at some example results. So if we look at the DeMarctech did some testing for SNIA, and they have their files are out here. You can look at their stuff and see what they got for collected data. And they have the SFlow data as well as the raw power meter data for the entire run. That's kind of what those things look like. You have timestamps and megabytes per second in and out. Down at the bottom you have your power meter. And notice it's got a date and time string over here. Can't highlight. So the power meter has a day, month, year, hour, minute, second, but the timestamp in the SFlow results is actually year, month, day, hour, minute, seconds. So you got to do a little bit of format changing to get these two to kind of line up. Now, if we go out and we look at the actual SFS results, these are not used for SNIA publication, but for the pre-calibration work. You can see that he did a load point of 9 with an increment of 9. So his business metric is going up in steps of 9 at a time. And you can see his requested operate and his achieved operate, which thank God it was the same, we're very close. And then you can see the average latency for each of those. So when it started out, he was under a millisecond. But by the time he got to the business metric of 90, his average latency is now 13 milliseconds. And if you would have gone up another 9, it would have been marked invalid because it would have gone outside the pass-fail criteria of the benchmark. So it would have, over on the far right-hand side, instead of saying VDA, it would say VDA, and then if it was invalid, it'll have space and then invalid beside it to tell you you've exceeded what the server is capable of doing. So we have this SFlow tool, and we have kind of a slightly modified version that Nick Principe from IX Systems has created for us. And this tool, it takes a couple of command line options. The first one's -4, which means TCP/IP version 4. The -L means I want to stick my output in a CSV file, comma and space delimited. And it will also put timestamps in each of the entries that are sprayed into that file. And then Nick Principe also created a tool which you can download from this location here called SPEC2014. So basically what this does is this is a tool that says I'm going to go read the SFS log file and I'm going to extract what time did it start the measurement, what time did it finish the measurement. And then I'm going to go look at your SFlow data or your power meter data, you can select which, and you can say, given that I know the start and stop time of the run window, the measurement window, find me all of the power meter or SFlow data that lands within that window and send it out to a file. So this, instead of having, your SFlow has been running for potentially hours, your power meter has been running for potentially hours. It ran through 4 different workloads. Each of those had 10 different load points. So you can manually go out and gather this stuff up yourself. Go look at the SFlow, the SFS logs, figure out the start, figure out when it ended the run phase, then go find those entries in those power meter and the SFlow data logs. Manually, you can do this yourself. The purpose of SPEC2014 is to try and automate that process so it's not quite so painful. All right. And then we're going to take, once we got the set of results that are within the run window. Then we're going to use Excel and some rather interesting mathematical magic to produce our megabytes per second per watt efficiency values for the peak load point of the run phase of each workload. So we ran 10 load points. Probably at the last load point is the run phase of the last load point is probably where you can expect it to have your peak efficiency. Okay. And I think now we need to have Patrick step in and talk about how you merge these things together.